Yesterday we were looking at the factor safety. I think you could see this matrix: inspectable, non-inspectable, and critical and not critical. So, we could decide a factor safety of whichever the category we are looking at. Further than this, API also has given some guidance on type of platforms. For example, failure critical, failure non-critical. You may have a platform which is unmanned, a platform has nobody living there, purely for the purpose of drilling. So, you may actually consider non-critical, because the critical with respect to not the safety of the structure. Actually, if you go back one step backward, it is critical with respect to safety of human life. So, suppose you have a platform where people are living there and the structure collapses or fails due to inherent deficiency in the structural design, then it is actually to be rectified. So, basically the critical or non-critical, the loss of life is to be avoided. So, that is why API has given a classification of structures class L1 to class L4, L1 to L4 depending on the criticality of the structure. So, you can choose L1 means is very critical, L4 just a secondary structure. You may have many secondary structures. For example, you may have a flare platform where I think I have shown you some structures where only flare boom will be there. There is nobody there, always is going to only exhaust or vent the gas and fire the gas. So, those type of platforms you do not necessarily to be designed with the factor safety of 10, because loss of life is definitely not there, but subsequent to the damage of the structure, if there is a vicinity, there is another structure which may actually have problem. So, you may have to consider not only the individual structure, but also the structure connected to the particular field in which these structures are located. So, basically overall you will do a risk assessment, which we call it quantitative risk assessment, and look at each of the component of the structure, and if that fails, what happens to the other part of the either that structure or the neighboring structure, come up with whether it is critical or not critical, what is the probability of occurrence, then decide which factor safety is supposed to be applied. So, this exercise needs to be done by the owner and the owner's engineer. Now, the API has not given mandatory that you have to apply 10, it is up to the designer to decide which component requires higher factor safety, which component may you can apply lower factor safety to just economize the design. It is basically that, because you could ask why we need all this. You simply apply factor safety of 10 through every part of the structure, then you do not need to argue, everything is very safe, but that is not going to be that easy, because applying uniform factor safety of 10 may actually require substantial design change, which may be not required and also not economical. So, basically what we have done is we have calculated the fatigue damage based on number of cycles of loading and number of cycles to failure, is not it? I think that is the fatigue damage. Now, this number of cycles of loading is based on certain duration of the design life. So, maybe 20 years, 25 years. Now, if you have this understood, basically n is coming from number of cycles throughout the design life. That means, the design life is included here, depending on what is the time duration, you may have number of cycles per year multiplied by number of years. So, that is basically the number of cycles down here is depicting indirectly the design life, is not it. So, basically you have that. Now, if you know what is the design fatigue damage, you can actually find out in reverse what is the design life. So, 1 by damage will give you the design life itself. So, that is what we are going to rewrite the equation basically after multiplying the factor safety, because what we have learned is factor safety is 2, 5, 10 whatever you require. So, basically the total damage is the damage you calculated from the ratio n by the allowable cycles multiplied by the factor safety. That means, this after multiplying by the factor safety you should keep it less than 1, basically that is the idea. So, suppose if you want to keep it under control, 0.5 if you limit, factor safety you will get 2, if you keep it 0.1, factor safety is 10. So, similar. So, basically that means in reverse you can actually find out the design life will be equal to 1 by fatigue damage, because the number of cycles applied is indirectly having the total design life itself. Sometimes why we need to calculate this, because many times the jacket is fabricated in the yard and then getting transported from the yard to the final location wherever it is going to be installed. And typical transportation, I think we might think depending on the location, for example, from Middle East to Southeast Asia or elsewhere, you could easily see that the transportation time is about a month, typically 4 weeks, 6 weeks, depending on the time. So, 6 weeks these jackets and topsides are going to be transported on the open sea condition, on a barge or on a ship. So, when it is moving, it is subjected to cyclic loads, which we discussed I think few days back, the different types of fatigue. Fatigue due to roll and pitch motion of the transport vessel. Of course, there is no direct wave loading on the structure, but the wave loading is on the ship, but because of the wave loading on the ship or the barge, the structure is subjected to inertia induced dynamic loads. So, that could cause fatigue. So, that is why sometimes we may need to find out total damage minus the damage from other sources, because already before the structure reaches the site, this is already expended, that means is already damage has occurred. So, you have to add that. So, many times transportation fatigue is becoming a very major issue, especially when you have a transportation longer than 2 weeks. Normally certification agencies, if the transportation is less than 2 weeks, you can ignore because the damage is too small, but in cases of coming from Southeast Asia to Middle East, normally take about 4 weeks. So, 4 weeks you calculate the number of cycles, it could be smaller, but unfortunately two things is a problem. Basically the sea state conditions can be higher, number one. Number two, the magnitude of stresses can be substantially larger compared to a direct wave induced forces. Wave induced forces does not depend on the weight of the structure, whereas the motion induced forces, as you can see, the inertia force is directly proportional to mass of the structure and the roll and pitch motion of the ship and cargo system. So, the larger the weight, you will see that the structure will be subjected to larger inertia forces. The stresses, when you compare that inertia induced forces compared to the direct wave loading, you will see that magnitude would be several times higher, and that may actually push you to have number of cycles smaller, because you have seen the SN curve. Larger the stress range, the number of cycles to failure will certainly come down. So, when you do this transportation, already some damage has already occurred. Now, when you go and install the jacket in the final in service condition, you can't allow the fatigue damage to 1, because already during transportation so much of damage has happened. So, that means you can only incrementally add, and that is what we are trying to find out, what will be the remaining fatigue life of the structure. So, you have some damage during transportation, go and install it, and you can calculate back the fatigue life remaining is x years. So, this is exactly the idea behind. So, that means it does not only, I have mentioned here transportation, from any other sources. If you have already got some damages due to or fatigue problem due to other sources of loading, then you just detect from the fatigue life at the final service condition. Many times we require to do this. So, basically I think in summary, you now should have an idea of designing a tubular connection for cyclic loads in terms of fatigue damage. So, what we did, we have actually learned about static design and cyclic design. Both seems to be a complete different methodology. One is based on the stresses applied and stresses allowable. The other one is based on cycles applied and cycles allowable corresponding to a particular stress range. Now, one thing we have not addressed this before we go to the tubular joints stiffened with other ring stiffeners or other forms of stiffening. One thing very important is a variable stresses applied to the structure. Basically what we have talked about, you saw that SN curve, all the time I am picking up a particular stress range, number of cycles. Now, all this relationship, the generation of SN curve was based on actually non-variable cyclic stresses. That means you take a specimen, fabricate and go to the lab, you apply constant stresses, means stress range is x amount, you just keep on apply that, and whenever the joint fails, note down the number of cycles that it has taken to fail, and then you go and repeat that for different stress ranges. Now, this is not the sequence that is actually happening inside. It is not like today only 100 megapascal stresses are occurring, and tomorrow 200, day after tomorrow 10. So, the sequence of loading is not exactly the simulation done by the researchers during generation of SN curve. Nobody could actually predict what could be the sequence of loading, small, big, it is not a sequence that you can predict. So, that is exactly where there is an uncertainty, which we call it variable stress loading, whereas in the simulation in the laboratory, either to generate SN curve or to generate any testing, you may not be able to exactly simulate what is happening in the field, because you will not be able to find out what is the sequence of whether the bigger stress range happening first, smaller next, or smaller first, and what sequence of stresses changing is not going to be easy to predict. So, this is one of the area where a lot of studies even now going on, basically stochastic modeling of stress range cycles, which you could relate directly to or very close to the field data. So, basically that is one issue still pending. Even today when we are designing as per API or DNV or any other codes, the variable stress loading is a parameter that has not been accounted in today's design practice, and that is why sometimes we use a probability based design, because at least some amount of variable can be brought in, but unfortunately API has not recommended yet, and basically we will have to wait for the next revision. I think 22nd edition of the API, the task committee has recommended probability based fatigue design. So, we have to wait and see, the code has not been released yet. We can stop there, and basically I think you should be able to understand and do a quick design. Three things in this module. One is estimation of fatigue damage based on number of cycles applied, number of cycles allowable, estimation of stress concentration factor given the basically the tubular joint geometry and the empirical equations from either FT mu or other equations. You should be able to go and compute and understand the variation of that SCF along the periphery of the card brace interface is not constant, and that you must be able to differentiate between the previous SCF equations given by API for simple, which is actually a constant SCF value for a single connection. There is no variation between card, crown point and the saddle point, similarly for the brace crown point and the, whereas the empirical equations provided by FT mu and others have differentiated that, but that is not adequate. We have to interpolate for quarter points by a linear means, basically just interpolate linearly. So, these three issues you should be able to understand and able to solve some problems. If data is given, equations are provided, I think you should be able to. And the last one is the combination of the stress concentration factor with the applied stresses to find out the maximum hotspot stress range. I think you should know what is stress and what is stress range. If it is a sinusoidal variation, you can multiply by 2, or otherwise you find out the maximum and minimum, the difference will give you the stress range. You should be able to go and read the SN curve to obtain the number of cycles to failure and basically find out the fatigue damage. You understand the idea, no? If the number of cycles is not given, applied number of cycles, for example, a hypothetical case, basically a wave is occurring in a particular site, wave period is 10 seconds with a percentage of time occurring say 70% over a year. If that is the only information given, you should be able to calculate the number of cycles, isn't it? Very simple. Total duration in a year multiplied by 0.7 divided by the wave period will give you the number of cycles. So, you should know how indirectly things can be calculated given the duration of design life or the time duration of the occurrence. For example, sometimes you may not be given full period of cycles, you will be given that wave data available is for 3 months. So, you calculate 3 months time divided by the wave period will give you the number of cycles occurring in 3 months, but then you have to multiply by the design life of the structure, which can be 25 years, 30 years, 50 years, then you will get the total number of cycles applied. So, you should start thinking rather than simply what we have learned in this few days course. So, you should just apply your mind. So, we will move on to the next topic in this. I think we should be able to finish this topic today. Basically, the ring stiffened tubular connections. Last time I think for static connection design, we have learned about reinforcing the joint because the chord wall thickness could not be increased for several reasons, which we have discussed last time. And now we have a problem of failure, maybe due to large stress concentration factor, large stresses. Now, what we need to do is we need to find out alternate means. One of the means is to stiffen the joint as usual, what we have done for the static design or static loads. So, you could actually put stiffener in this fashion, a typical arrangement, just to get an idea. But what happened is, when you designed for static load, we never bothered about the stress concentration factor. What we were always looking at is the stiffening to avoid local failure of the chord from ovalization or by local punching. Whereas, here when we have done this exercise, we need to make sure that the stress concentration between the chord and the stiffener itself within the inside somewhere here at the inner face has to be made sure that it is not governing the design, because you always have the stress concentration factors calculated for the brace and chord interface. But if you forget the stress concentration factor under the chord inside, and you may actually start or initializing a failure in that particular location. So, one of the problem is this connection cannot be inspected. Once you have installed this ring and close the tubular, nobody is able to go and inspect inside. So, it is an uninspectable joint, number one, and that means the risk is slightly higher. You may see that factor safety required for such type of joints should be increased, because once you install, because this tubular is not open like this, it is welded to another column or a brace, and this side is closed. So, nobody can go inside and verify during the life. So, that is one of the problem. Basically, we try to avoid, many of the owners and clients and consultants do not recommend stiffened joints, something like this, unless otherwise is the last resort that you have no other choice, then you can use it, but otherwise normally not recommended. The Lloyd's register actually has given some recommendations, basically a modified form of FTMU equations. So, you have a FTMU equations for unstiffened joint, and there is a correction factor. This is a simple idea, like what I was trying to explain the other day, unstiffened tubular connection strength and multiply by a enhancement factor for stiffened joint. Similar here is exactly reverse, or it can be forward depending on the location. For example, this stress concentration factor between brace and chord can be reduced, because the local ovalizing effect has been slightly improved, but then as long as the stress concentration factor between the chord and the ring is smaller, is not it, because then you are actually reducing the total the effect. Otherwise, you may actually reduce the stress concentration factor on the brace chord interface, but the stress concentration factor just inside is very high. In any case, is not going to be useful. So, API has not given mandatory that you only have to use Lloyd's equations. Normally, it is recommending that you can use specific finite element analysis. The reason is such type of stiffening is not very common, not recommended, and when you have a large problem that you could not resolve, you have to provide rings, and that means it is only a specific cases. So, it is leaving to the designer that either you can use Lloyd's equations or you can generate your own SEF by doing a detailed finite element study, and many times a minimum SEF of 2 for axial and basically 1.5 for other locations is recommended, and basically these minimum requirements is given because if it comes to be less than that. So, other than that, the joint design is exactly same as unstiffened joint, only replace the stress concentration factors, but there is something is not right. Basically the effect of stiffening has not gone into your actual analysis and stress calculations, isn't it? You only have taken effect of the stiffening in the stress concentration factor only. There is no reduction in stresses or alteration in stress pattern because of the presence of, and that's why that's exactly why many times the recommendation for ring stiffened joint is not very good, because still a lot of studies are going on, many research is being done, but unfortunately nothing has come out as a usable form for design. So basically the stiffened SEF is unstiffened SEF multiplied by the ratio of measured SEF, or you can do a measurement or you can do a FE analysis, and unstiffened joint, stiffened joint and versus unstiffened joint. So as the ratio is less than 1, you will see that you will always have a slight reduction in the brace cord interface. At the same time, if you are able to get the SEF at the ring versus the cord is less than the values given for this point, then you are safe. That means you are going to reduce the SEF by some amount, but if you have forgotten to do this, probably problem. And many times depending on the joint configuration, depending on the type of, whether it is a T section or a simple flat bar, the stress concentration can be different. And also you may have to look at the stress concentration factor at the interface between this flange and the web at this junction, which is also sometimes can be very large. The next one is the stress concentration factor for the grouted joints. So now you just look back what we did for the stiffened joints in static design. For example, ring stiffened joints, we simply replace the thickness with the equivalent thickness. That was one of the easiest method which we are talking about. There were four or five methods I was talking about. One of the method is just replacing the equivalent thickness, and the other methods were trying to do analysis using ring formulas and shear capacities. I think there were 4 or 5 methods, no. So among them, replacing the thickness with the equivalent thickness was such a simple method, because you do not need to do anything else. The effect of the ring is replaced by increased wall thickness of the cord member, isn't it? So same thing API is recommending for grouted joints here. Only thing is it is not using the SRSS equivalents here. Based on some amount of testing, is recommended that the equivalent or so called effective thickness is taken as 0.035 times diameter plus 0.93 times the cord thickness. Basically pile is inside, no, and the cord is outside. So such an equivalence is based on predominantly several testing, because it is a grouted joint. The behavior against fatigue is not exactly like a static loading, because static loading is going to be one magnitude applied constant, whereas here you may have tension and compression. The grout may actually, what will happen to the grout? After several cycles of variable amplitude of stresses, the grout may actually start cracking, get separation. So the inner tube and the outer tube may get separated, grout will not be effective depending on the magnitude of stress. Now the problem is when that magnitude occurs. If a larger magnitude occurs in the starting few cycles of the loading, the remainder of the life reduced thickness will be there. Whereas if the same thing exactly reverse, there are so many smaller cycles of loading, the magnitude is small, but only the larger magnitude occurs at the tail end of the life, which we do not know. This is one of the major problem, and basically whenever we use this, if you get the thickness equivalent or thickness effective larger than 2 times the thickness of the outer shell, I think that there was a limitation in the static design also. Normally we do not recommend. For example, you go and calculate using this formula, if the cord thickness is 50 mm and the equivalent thickness or effective thickness comes 150 mm, we should not be using 150, we should be using 100. So basically that limitation is by experience, by a lot of references, but API for static design has given 2, whereas here for cyclic design it has not given any reference here, but for sure you should not be using the SRSS which was permitted in the static design, square root of TP square plus TC square we were using, no. So, that you should not be using here because of the grout failure, changing direction of the stress or the magnitude of stresses from positive to negative. A minimum SEF of 1.5. So, now you could see that when you calculate a stress concentration factor, you may actually get less than 1.5 at some locations, 1.2, 1.3. So, that is why every class API gives you a recommendation that minimum SEF use 1.5 if you get less than 1.5. So, these two classes of connections, ring stiffened connections and tubular and tubular inside with grouted annulus, it is a special type. Only what we are doing is we are replacing with either the increased or reduced stress concentration factor or increased chord wall thickness. Once you do this, then the problem becomes same as the simplified tubular joint where there is no stiffening is done. So, just a substitution of parameter, then you treat the problem same as the conventional joints. Now, once you have come to this stage, that means you have designed, you have fabricated, but there was some changes required either to improve the design life because the wall thickness provided has got certain design life, but unable to satisfy the design requirements. When it will happen? During the design. Normally it does not happen because if you have done a proper design, it should not be a problem. But what happens is there may be several restrictions given to you. For example, you have a jacket leg say 2 meter diameter. What could be the maximum wall thickness you can go for a 2 meter diameter? You should be able to get the idea, no? 2 meter diameter, what should be the maximum wall thickness you can, what will be the minimum D by T ratio you can apply? I think nobody seems to be have any idea. The minimum D by T ratio that you can go is 20, isn't it? Maximum D by T ratio is 60. When you are asked for a maximum wall thickness, that means you have to use the minimum D by T ratio. So, 2000 mm divided by D by T ratio of 20. So, you can go for a 100 mm thickness, isn't it? So, you have selected your pile, you have selected your leg, you have designed all your system, everything seems to be fine except few connections in the leg, fatigue problem is there or the design fatigue life is not satisfied. So, I want to increase the wall thickness to 150, but I can't increase, the D by T ratio is supposed to be greater than 20, cannot be less than 20 for obvious reasons. I think you have already hopefully remember why we can't have a D by T ratio less than 20, because we cannot fabricate, we cannot roll, because rolling stresses will be very large because of very thick plate. When you try to roll to 2 meter diameter, you may get into a residual stresses excessively high and the machines to roll such a thick plate may be not available. Hopefully, I think you have to recollect if you do not remember. So, basic idea is we cannot go beyond 100, but design is not satisfied, but fortunately design is satisfied everywhere except this fatigue at that particular joint, isn't it. So, we do not want to go and increase the diameter to 3 meter just for one joint or few joints which are giving problem in design against cyclic loads, but everything else is fine. So, that is a situation when you will start thinking alternate solutions to, instead of increasing from 100 to 150, let us see any other alternate idea which can resolve this problem. Changing material, isn't it one of the idea, you can just simply go for better material by which it can provide you the required strength, but fortunately all the design requirements satisfied including strength except the fatigue. Fatigue changing material is not going to help because you have only steel of variety of yield strength changes. Unfortunately, the fatigue is not at all related to strength of the material, it is basically a material characteristics against crack. So, that means even change of material is not going to help. So, that is the time we need to start thinking of any other idea other than just only the strength, which can help us increase the design fatigue life. So, some of the ideas is providing rings. For example, we just learned by providing rings you are reducing the stress concentration factor, but if you have a jacket leg with a pile inside, can you provide rings? We cannot provide rings. You provide rings, you cannot do the piles. So, that is exactly the problem. So, all other ways of doing it is externally, something to do with the connection between the brace and the leg. So, that is what we are going to just see how we can improve the design life, reduce the fatigue damage. So, that is the idea. Now, we have learned about reasonable understanding of the stress concentration factor and why it is occurring, where it is occurring, is not it? Basically, it is occurring at the interface between the weld, between the brace and the cord. So, that is the area we are going to focus. So, if you look at a simple picture, something like this, I have shown you some photographs, two situations, one is the 20 degrees, the other one is larger than 90 degrees, something like this. If you take a tubular connection, on this side will be less angle, the other side will be larger angle, is not it. So, basically both the situations you can see first this particular connection where the angle of the wall thickness, this is just part of the thickness. So, basically if I draw a picture, it is something like this in a larger view. So, if I have a brace connection something like this, maybe just exaggerate, something like this. So, in this area and in this area. So, basically situation 1 and situation 2. So, on the right hand side we have situation 1 where the angle is larger than 90 degrees, and basically you see here multi-pass welding. I think by this time you have an understanding how the welding is done, because the gap is about probably 50 to 60 mm. So, every time you go around one cycle of welding, second cycle of welding, third cycle, fourth cycle, you will be able to understand its the weld deposits in this kind of form. And if you really see in a close view, you will see that surface is not that smooth. Now, if you look at this, when you just go into this particular junction, just the connection between the brace and the weld, you will see that the surface is not that smooth, and because of that you will see a increased value of stress concentration at that location, and along the weld you will see a several changing surfaces. And finally, when it comes to connect to the that location, it is also a notch, basically a change in the angle of this much, it is not smooth enough. Now, if you just try to do grinding by means of removal of the weld material to form a smoother surface, just take away this material to get the surface tangential to the brace wall thickness and come and joint nearly tangential to the cord wall thickness. It is not drawn exactly 100% correct, but if you are able to get that curvature correctly, join smoothly with the brace and the cord, you could reduce substantial amount of stress concentration factor. This has been proved by several model testing as well as by FE analysis of the weld, and that is why this is one of the best method from a stress concentration factor of nearly say 9 and 10. Most of the braces, if you calculate, you will see the SCF of 9, 10, something like this. Now, if you are able to reduce the stress concentration from 9, 10 to 2 and 3, you have a threefold reduction. When you have a stress concentration factor reduction in threefold, you will see that the design life can jump very fast, which is very good idea. And also when you do this grinding, you have improved to another thing, the SN curve. Remember, SN curve includes some part of the weld connection, some part of undercut, some part of the profile of the weld is already incorporated in the SN curve. So, that is why you will see there are two SN curves provided by any code, normal SN curve or improved SN curve. The improved SN curve is for profiles of this nature, you know. So, basically there are two ways coming in together. As long as your weld is nicely smoothened, then you can improve the fatigue life substantially. And one of the area is, how do we do this? How do we cut this is a very big problem. It is not going to be that easy, because when you are making a cutting, you may accidentally cut your parent material, and this is something has to be remembered. So, that means it is a manual method. So, most of this grinding is done by manually, slowly, not by simply taking one cutting machine and then cut away the material in this profile. It is not feasible, because the surface is so complicated. So, that is why normally not recommended. Normally, why not recommended is basically doing this is a very troublesome process, because time consuming. For example, if you remember, if from here to here the distance could be 100 mm or maybe less than that, 100 mm all around the brace, and going and taking away the material by simple manual grinding can take several days. One joint can take several days, and that is why not recommended. But when the recommendation comes into picture only when you have choice, but when you do not have choice, because no other methods seems to be giving you the design requirement, then you will implement this. So, we call it profile grinding. Sometimes the terminology used in the industry is called profile grinding. What type of profile? It is not that I just go there and just grind it according to my wish. It is not going to be acceptable. There are several requirements given in API. What should be the radius of this curvature at the joining point and the angles? Some simple ideas are given. Normally, we do a coin test. You know, if I do a profile like this, we actually fit, after profiling, we actually place, you see here, this is coin or disc. For a given weld profile, after grinding you take the disc number 5, you just fit it in. If it fits and rolls properly, that means the profile is done according to the requirement. So, basically coin test or disc test is a method to check the curvature of joining profile from the weld to the card or weld to the brace. So, basically that is one of the tests normally done, and just to make sure that the profile is in accordance with the requirement of the codes. So, this profiling of weld surface is to be recommended as a last resort that the design is unable to satisfy, or other ways, smoothing of weld caps. Basically, that is one of the area where can give you a considerable reduction in stress concentration factors, especially when you have a variable thicknesses, thickness smaller, thickness bigger. When you try to join, if you smoothen the weld by means of tapering the thicker material and joining here, instead of just keeping it like this and make the joint, which is going to give you a larger stress concentration factor. But then the tapering, the codes recommend a minimum tapering is 1 in 3, the slope, sometimes 1 in 2 or 1 in 3, because 1 in 3 means more work, 1 in 2 means less work, 1 in 4 means so even more length of cutting, which many times is not preferred, because lot of grinding work, especially manual grinding. The other forms of basically improving design life is welded toe grinding. After doing this profile, you go to the end of the weld and try to remove any discontinuity, you know, at the toe of the weld. There could be a small gap which can be removed by toe grinding. Hammer peening of the welded toe, just hammer it so that the loose material, if any, will actually come out. So, though these two are given as an option, quantification of such improvements are very small. So, API does specify that you could use one of these methods, but not giving you the clear idea how much improvement that you can actually get. Whereas, the smoothing of weld caps is similar to the weld profiling, basically the surface profiling. All these 4 methods are mentioned in API, but directly giving the recommendation to calculate the design life is only for the first one. The profile weld, there is a formula to calculate the increased design life. The last one before we finish the weld improvement is basically the post weld heat treatment, which I think I mentioned about it last time. After you fabricate the joint, because of the inherent residual stresses, there could be potential cracks initiate. So, what we do is we take the whole joint, take it into a larger oven and heat it, relieve the stresses. So, that is one of the method which is adapted like 30-40 years back. Some of the joints fabricated in Gulf of Mexico for our big jackets, 450 meter jacket, they had a larger problem of weld cracks even during welding itself. So, what they did was actually heated the material and basically after welding and heated the joints and then cool down at a controlled. So, basically post weld heat treatment is nothing but trying to relax the weld after welding. So, that means you will heat the total assembly. That means, if you fabricate a joint of 3 meters by 2 meter diameter with so many braces connected, and the whole assembly has to be taken to a shop where you can heat it to 1500 or higher temperature and then allow it to cool very slowly, not at the abrupt change. This post weld heat treatment normally not recommended, because not everybody has the facility to heat and cool down, because you need to create a big oven. Whereas, normally used in the mechanical pressure vessel industry, normally people use this when the pressure vessel is very thick, they fabricate the pressure vessel and heat it and cool down, because pressure vessel carrying large pressures, you do not want to have the higher residual stresses. So, among these the first and the last, the first one and the last one is inherently easy to apply the method to improve the design life, whereas the others, though idea is given, but use of them for real purpose is very limited. I have given 2 example problems. Hope you now you get the idea to go through. I think all of you got this slides, no? So, now you have learned about the process by which we are doing the fatigue design. So, now if you read this, you should be able to understand, and probably we will be discussing this in one of our tutorial class, So, in brief, what I have asked here, we have 1 minute to go. So, basically is a tubular T joint, and basically what has been given is the wave height, wave period, percentage of time, stress magnitudes for each of the cases. So, basically it is a complete scatter diagram including stresses is given to you. Of course, we could ask you to calculate the stresses, but that will take several days, because you need to do a computer analysis, come up with the stresses, those stresses will be calculated and used. But in here for examination purpose, the stresses also given. So, that means you have a tubular joint, applied stresses on a brace for different wave heights is given to you. You understand the idea, no? And wave period is given, and percentage of occurrence for each of the wave period and wave height is given. Now, you could calculate the number of cycles, I think, because percentage of time is given, period is given. Of course, I have given you the period in some range, So, you need to go for a mean period. So, just average period, and then stresses are given. You know what is the geometry of the joint, calculate the stress concentration factors, and then stresses are known, multiplied by stress concentration factor, you can get the stress range, and you have got the equation for the SN curve. Go and calculate the cycles of the failure to the joint and calculate the fatigue damage for each of the C state and cumulatively add. So, it is a very simple straightforward problem. There is no hidden issues down there. Another problem which is similar, except that this is due to transportation, you know. So, you read it and we will do something in the similar type will be given in the tutorial.